I hope 8.1 went okay for everyone. It is sort of a transition into a new way of thinking in terms of what logarithms are. The key is really to always remember that they're the inverse of an exponential function. So we spent a lot of time in grade 11, an entire chapter doing exponential functions. And the keys to many of these questions is remembering all the things we already know about exponential functions. So if you have to review a little bit about exponential functions, then that's advised to make it a little easier. Okay, 8.2 is actually super straightforward in terms of things we already know how to do. We know how to transform functions. We know where a vertical stretch or a horizontal compression or a shift left or a shift up, we know where all those take place. We spent so much time in grade 11 doing it. We spent a lot of time in the beginning of chapters transforming the new functions that we looked at. And this is going to be the same thing, but we're just going to transform logarithmic functions. So again, the key is going to be to remember that a logarithmic function in terms of what its graph looks like is the inverse of an exponential function. So that's how I'm going to basically answer all the questions, is really playing into that idea that it's an inverse of an exponential. So the first thing to look at is, if this is my exponential function, y equals 10 to the x, and I wanted you to graph that, you'll remember in grade 11 when we graphed exponential functions, you had to come up with key points for every individual question you encountered, and the key points would be different depending on what the base was. It's not like sine or cosine or some of the other functions where we said these are the x values you're going to sub in. For this, we always subbed in x values of -1, 0, and 1, and then you had to figure out what the exact y value was based on that. So more about that when we get down here. So what you should be able to do from 8.1 is transition from exponential form to its inverse. Remember, the base remains the same. So this is base 10. Well, this is log base 10. Okay? The x goes over here, y on both sides. Now, if they are true inverses, that means that there's an interchanging of x and y values, and interchanging of x and y intercepts, and interchanging of x or y asymptotes. Everything gets switched. So some things to remember about all exponential functions, not just this example, is that they have a y-intercept of 1. That means all logarithmic functions that haven't been transformed have an x-intercept of 1. As far as their end behavior, as x is approaching infinity, so remember what this looks like in general. If I just draw a tiny sketch, this is going like this. So as x is approaching infinity, getting larger and larger, so is the function. Well, if I'm going to look at a logarithmic function, which I know is, remember, a reflection of the diagonal line, then this is now kind of over here. As the function is approaching infinity, x is also approaching infinity, so it's just replacing which order we did them in. Okay, and in this one, the x-axis acts as an asymptote. In this one, the y-axis acts as an asymptote. So that's actually a very important thing. So when the x-axis acted as an asymptote, that meant that y equals 0 was the asymptote, and it was right across here. Okay, now in this one, if the y-axis is the asymptote, then the original asymptote is x equals 0. So a line right up there. So before you transform it, that is the asymptote for all natural logarithmic functions. Okay, so in their natural state. Once we move them left and right, well, that's going to shift the asymptote. Okay, so that, I don't know what, there's an alarm going off. That's the main thing we have to know. So steps that we're going to use in order to graph, and this is where I want you to do it. It's off. Okay. Start with the key points of the inverse function. That's the exponential function. So if you look at what your inverse would be, okay, if I want to graph this, I would look at my inverse, start with those key points, then interchange them to put them into this form, because we don't really know what to do with how to look at substituting things in. We haven't looked at our calculator and how to plug those in yet. Once we interchange them, we can apply the transformations naturally. Okay? Again, the asymptote is x equals 0 unless you shift it left and right. If the whole function gets shifted left and right, so does the asymptote, so that will change. The range of this function, so up and down on the y scale, is always y belongs to real numbers. The domain will be restricted by whatever the asymptote is, so just realize that. Okay, so this blue stuff right here is fairly important if you want to kind of write that down. It's not in the note. It's more my method for doing things. I hear my kids screaming, but I don't know what about. Okay, so I want to do the two examples that are in the note, but I'm going to do them a little bit differently. Like, I like to do the graphing questions maybe in a different manner than what's on the note. So I would have taught it a little differently if we were in class. So the first question wants us to sketch y equals -2 log base 10 x minus 4. Okay, so the keys to these questions are going to be to follow the exact same methods that we used before. First, you have to identify what is the base function. So what is the base logarithmic function before any transformation has been applied? So it always will just be a log. The base remains the same, and you just consider an x. So that's the base function. Of note, and this is important, you need to realize that the inverse of this is y equals 10 to the x. Okay, because that's going to be important for graphing. So like we did in 8.1, you have to be able to interchange back and forth from the logarithmic function to its inverse exponential function. Okay, once we know what the base is, we should list what the transformations are, and you're used to me doing this. So we look, and there are 1, 2, 3 transformations that stop this from just being log base 10 of x. Okay, so are there stretches or compressions? Yes, vertical stretch by 2. Okay, that takes care of that one. Is there a reflection? Yes, vertical reflection. Is there a translation? That accounts for up and down or left and right. Because this is in the brackets, that's considered inside the function. So it's actually a horizontal translation in this case with the negative, right 4. If there was a number on the end, it would be going up or down. Okay? So once we know what is happening here in terms of the transformations, we can start building our set of key points. And this is where I sort of said, you should look at this and remember what were the key points. And you can do this on a scrap piece of paper on the side if we were just looking at the exponential function. So the exponential function, if you were in my class, I would have said, put -1, 0, and 1, and then see what happens. So when I put 10 to the -1, I get 1/10. 10 to the 0 is 1. 10 to the 1 is 10. So you're going to take this. These were your original key points for the exponential function, and you're going to interchange them. So we're going to start, for our purposes, with the key points interchange. So 1/10, I'm just going to write it as 0.1 for graphical purposes, and -1. I just switched where the x and y were. What was a y now became an x. What was an x now became a y. And I'm going to do that for all 3 points. Okay, so that starts as our base. From there, we just apply the transformations like we always would. You no longer need to look up here at what this logarithm is, going, what's going on? You knew what an exponential function looked like. You interchange the points as your starting point, and then you follow the rules. A vertical stretch by 2 would mean I'd multiply the y by 2. Okay, a vertical reflection would mean I'd take that exact same y column and now multiply it by -1. So this becomes 2, 0, -2. And the last thing, going right 4, means I will add 4 to my x's. So I get 4.1, I get 5, and I get 14. Now what we want to do is graph, obviously, the outside columns. So we look, I have to go up to at least 14 on my x scale. This block doesn't work. So I'm just going to go 2, 4, 6, 8. Obviously my graphs look terrible. And then on my y scale, I have to go up to 2 and down to -2. And that should cover what I need. Now, some important points. I said originally on a logarithmic graph, the asymptote will be on the y-axis, x equals 0, unless we have a horizontal translation left or right. We translated right 4 units. That means the asymptote is also going to translate right 4 units. So before I even graph, I'm going to go ahead and put that asymptote there. I know it's going to be there. Now when I graph, it's just a matter of plotting my 3 points and making sure it makes sense. So I have 4.1 and 2 right there. I have 5 and 0 right here, and I have 14 and -2. And what you're really looking for, to make sure you didn't make a mistake, is does this make the exponential shape? Yes, it's going in opposite directions because it's the inverse, but it's still going to be that general shape where you're approaching the asymptote and then you're slinging sort of in the opposite direction. So this is what the final graph would look like. And if you wrote on it to get full marks on a test. Okay, it looks very similar to an exponential because it's the inverse. It's just a reflection of that line y equals x. But this is what the logarithmic graph looks like. Okay, the last thing is to state the domain and range. And the one thing I pointed out, that the range for all logarithmic functions will be y belongs to real numbers. Notice it's going to infinity, and it's very slowly, but approaching negative infinity. The domain will depend on where your asymptote is. So you're still going to put x belongs to real numbers, but notice x strongly has to be greater than 4. Not greater than or equal to, greater than. It can't touch that asymptote. Okay, I do not think this is overly difficult. I think you have to take this step right here of recognizing what the inverse is, making yourself a little set of key points somewhere on the side. Use -1, 0, and 1 as your x always. Plug them in to find out what your y's are. Swap them, so interchange them, and then apply the transformations. Okay, it's not a new concept. It's just one extra step to what we could do in grade 11 exponentials. Okay, the second example goes the other way. They give you the transformations and you have to come up with the formula. So in the question, I'm just gonna write down what they list in the question as the transformations. With the graph of the logarithmic function, so the base they tell us is y equals log x base 5, right there. Vertically compressed, so this is what they have. Vertically compressed by 2/3. Horizontally stretched by 4. Reflected in the y-axis. It has also been horizontally translated so that the vertical asymptote is at x equals -2. And remember what that means. A vertical asymptote at x equals -2 means it has shifted left 2. That's what this is telling us. Left 2. Okay, so be careful. Same with this. A reflection in the y-axis means it flips over the y-axis. It's actually a horizontal reflection. Okay, so just look at that. In the y-axis means it flips over the y-axis, so it's actually affecting x values, so horizontal reflection. So be careful, because sometimes the wording is a little bit funny. And vertically translated 3 down. Okay. Write an equation for the transformed graph and state its domain and range. All right. So if this was sort of a generalization of things, log, whatever your base is here, I'm just going to put log b because this number is going to change all the time. If I was going to write this in a form that kind of looked at everything, we can have a plus or minus out front. We can have a vertical stretch or compression here. And then, I should really write base here. I'm just going to put the word base here. Because here I'm going to say, well, what if I put a plus or minus some horizontal compression factor, x, plus or minus some left and right movement, I'm going to call C, and then at the end, plus or minus some vertical translation, D. So that's really, all of these could be applied at any given time to a logarithmic function. You keep the log where it is, you keep the base what it is, you keep the x what it is, and these are where the transformations are being applied. In this specific one, it says we have a vertical compression by 2/3. Well, vertical compression by 2/3 is going to go out front. Okay, now we know this has to be log base 5, so we put the 5 there. A horizontal stretch by 4, shows up in an opposite way. So you actually see a 1/4 here, but it's a horizontal stretch by 4. It also has a horizontal reflection, so there's going to be a negative in there. Left 2 means it appears as a positive inside the function, but it's actually moving left 2. And down 3 means you'll have a -3 at the end there. Okay, so all of these are being applied to this base function, log x base 5. Okay, so just be aware, nothing is changing in the way. The wording is a little bit trickier. In terms of domain and range, we've discussed the range is always y belongs to real numbers. The domain is dependent on the vertical asymptote. So because it's at x equals -2, think about what's happening here, because you also have to look at, because it's moved left 2, I just want to make sure we do this the right way. X is going to be less than -2. Because once you reflect it, then you're changing what would have naturally gone this way. It's been reflected, it's now going this way, so it's actually less than. So look out, normally it would be x is greater than 0. As soon as there's a horizontal reflection, it changes the sign to less than. As soon as there's a left and right movement, it changes the boundary of your domain. Okay, I truly think 8.2 is not going to be super difficult for us. A lot of the skills we already have. So you should look at this and say, great, graphing, I can handle this. I'm totally okay with it. Okay, I'm going to keep rolling today, so I might be in this outfit for the rest of the lessons this unit. Okay,